Hello. Yesterday in class we talked about Corey's synthesis of Salinosporamide A. And I wanted to spend a little time talking more about that because I think I rushed that at the end of class yesterday. So I wanted to again go through the retrosynthetic analysis that we could do and also think about identifying steps in the paper where we can see which atoms were added in the total synthesis. All right, so thinking about retrosynthetically and then doing some analysis of the forward synthesis. All right, so I have the structure of the molecule up here, and I want to go through the retrosynthetic analysis like we did in class yesterday, but maybe take it a little slower and talk through it a little bit more. And so what I want you to do when you look at a molecule like this is think about, which bonds do we know how to make? And think about retrons, which functional groups tell us how they were made, things like that. And I think we did a nice job with this yesterday, but again, just to go through it one more time, if we think about our retrosynthetic analysis of this molecule, hopefully our eye is drawn to the two most reactive functional groups, the fact that we have a primary chloride and the fact that we have a strained cyclic ester. Cyclic esters are known as lactones, so we have a strained lactone. So those are probably the two most important functional groups that we're going to disconnect first, things that we would make at the end of the synthesis. All right, so those would be the bonds we would identify, we would make right at the end of the synthesis, again, because they're quite reactive. We know how to make primary chlorides. We make those from primary alcohols, treating with SOCl2. And we know how to make esters, right? We can use carboxylic acid plus an alcohol, Fischer esterification, acid chloride plus an alcohol, things of that sort. So let's draw what we would get if we would do those disconnections. All right, so that would leave us with this molecule. Again, we've converted the chloride into a primary alcohol. We've converted the lactone into a carboxylic acid and an alcohol. All right, these are both things we could do in the forward direction. All right, we know the chemistry to do that. Now, thinking retrosynthetically, we have a lot of reactive functional groups at this point. We have an NH of an amide. We have 1, 2, 3 alcohols and a carboxylic acid. Those are all going to be reactive, right? And as we think about going backwards in the synthesis, we're probably going to think about these things as being protected, leaving only one functional group unprotected so we can do chemistry on it, all right? And I'm hoping that when we look at this, we see this group up here, this cyclohexane ring, hexene ring, as something that we're probably going to want to add to this molecule. Right, and we recognize that it's attached to a secondary alcohol, right? And I hope when you see that, you think about ways that we could make that bond. So what we're going to do going backwards is to protect a whole bunch of things here and then think about chemistry at this position, all right? So let's just use generic P as a generic protecting group. It doesn't really matter right now what that is. Again, we're thinking retrosynthetically here. So let's just say we're going to have that nitrogen protected as something. An alcohol protecting group. Another alcohol protecting group. Let's say that the carboxylic acid is going to be protected as an ester. We'll just put an R group there for generic ester. And we'll leave that one secondary alcohol unprotected so we could do some chemistry at that position, right? And so hopefully we're now thinking, okay, if this is a secondary alcohol, we could do a Grignard type reaction. We could add this piece to an aldehyde, for example, right? And that is exactly what Corey did in the synthesis, right? Was to say, we can easily make that 6-membered ring into a nucleophile. that can come from an aldehyde. That's going to give us a really nice way to make that bond. Right, and for us, we would probably say if we had a Grignard reagent, we could add a Grignard reagent to that aldehyde. If things go well, we can get selective reaction at the aldehyde instead of at the ester or at the amide carbonyl. And that's exactly what Corey did, right? Was to say that aldehyde is going to enable me to make that bond, all right? And then the final disconnection that we would probably make, and again, it's going to be more complicated than this in the synthesis, but you'll see that it's similar to this when you look through the paper, is to say, look, amide bond, right? We know how to make amide bonds, right? Carboxylic acid and amine. And again, we're either going to make that carboxylic acid into an acid chloride or some other activating group. But amide bonds are bonds that we definitely know how to make, right? And that enables us to take this really complicated molecule with lots of functional groups spread around two rings, to break it open. Now we have one ring, break it open one more time, and we'll get an acyclic molecule, right? And so what will this end up looking like? So we'll get back to something like that. Again, an acyclic compound, where going forward we could imagine making that ring by making the carboxylic acid into an acid chloride and forming the amide bond. Lots of functionality, bunch of stereocenters. And so the interesting thing is to think about, how might we do that, right? And we'll see how Corey ended up doing that. But this sort of retrosynthetic analysis using reactions that we know is not too far off from what Corey actually did in the synthesis. All right, so now is a good time to start looking at the actual paper to see what Corey did in the synthesis. And I want to do one more thing before we close, which is to look at that forward direction and have you think about some things as you scan through those reactions. All right, so grab the paper, and what I want you to do now is to number all the atoms in the molecule itself, and then we'll look and see where those atoms come from in individual steps. So if we number out all the atoms in our target, right, it's really interesting to have those things numbered out and then look in the paper and say, where do all those atoms come from, right? So if we start numbering this, right, and it doesn't really matter how you number this, right? So just pick a place to start. So I come up with 21 non-hydrogen atoms in Salinosporamide A. All right, so I've numbered them out there. And the interesting thing to think about is if you pick up the paper and you look at each step, try to figure out, where do these things come from? Because if you look at the starting material, right, Corey's essentially got a protecting group on the nitrogen to start. All right, that's what he starts with, all right? And the question is, which atoms do we have already right here, all right? And if we take a look at this, we can see that we have nitrogen 7, right? That's carbon 8, carbon 9. The methyl is carbon 10. The carbonyl out here, that's going to be one of our 2 carbons here, 12 or 14. Right? Sort of interesting to think about which one it's going to be. If you follow through in the synthesis, right, you can see that that ester is going to be carbon 12, right? And then the oxygen out here, right, that oxygen is going to end up being oxygen 11, right? So we have 1, 2, 3, 4, 5, 6 atoms of the 21 that we need. Right? And so the interesting thing that I want to encourage you to do is to start going through the synthesis and figure out, where do the rest of the atoms come from, right? We've got 6 of them here. As we roll through, where do the rest of them come from, right? And that's a really interesting thing to look at, trying to identify where certain things are. And so I want you to try that, right? And I think what we'll do in class on Friday is we'll pick this up, and I want to see how many of these, hopefully all of them, that you can figure out the origin of where these atoms come from in the synthesis itself. All right, so we'll pick this up again in class tomorrow.